Okay, so we had a little interruption with our practicum, but if you remember, we were talking about the transformer architecture, and we have finished going over all the ins and outs of the transformer. And basically what we have focused on is the self-attention mechanism, which have been slightly tweaked for in the decoder part, where we have masked the ability to look at the future tokens. And we had that cross attention that went from decoder to encoder. But all of that was to basically handle longer text better than a recurrent neural network that in theory should have capacity to, in its hidden states, to remember everything we have seen so far, but in practice, that usually happens. With self-attention mechanism, when we are at the end of our input, we always have this parallel process where through self-attention, we can look into the beginning of our sequence. So in that sense, it handles longer text better than recurrent neural network. We have seen that we have these many transformations that consider what else in the input is there, right? So if we have a word that has multiple senses, we have an opportunity to disambiguate it again with the self-attention mechanism. And finally, we have also introduced the encoding of a token order. So all the recurrent neural network had that by default. Our previous neural network, simple feed-forward layers with averaging of embeddings didn't. And by introducing positional encoding, for example, with the rotation in our queries and keys through rope, we are able to encode order of tokens. Now, Transformer has been introduced in 2017, and to me, it's kind of a miracle that it's still around. Prior to that, we have always had these architectural major changes happening since the deep learning has took off around 2014. However, there are some tweaks to this architecture that you will see today. Some of them I have introduced. So for example, we have talked about row in place of positional embeddings. We have also talked about other way of doing layer normalization. But there are some other little changes. If you're interested, I highly recommend reading this blog post that goes nicely through major changes in the transformer architecture as it's used in current large language models. So for example, you will see that instead of using GLU as a activation, we are going to use something like Swift GLU. And there is a lot of changes happening with the attention to make it better for longer and longer texts. Feed-forward layers have also sometimes been changed with the mixture of experts or sparser representation. So there are kind of non-trivial amount of changes. We won't go through all of them because we simply need to go to more NLP parts of this course as well. But if you're interested, I highly recommend reading this post. Yeah.
There are like specific problems with transformers that have been identified in the community that are being actively looked into?
Yeah. So there is a research question, which is there something inherently wrong about transformers for certain kinds of problems? So one of these questions is there something inherently wrong in transformers to do tasks that require lots of compositionality? And there is theoretical work that shows, yes, if you want to do compositional tasks that have a lot of depth, transformer by itself are limited. And there are other examples of that. So there are families of problems where transformers have been shown to simply architecturally not be capable of doing those problems. So I can send you some papers later on. So definitely there are problems with the transformers. I don't think anyone believes that that's the end, right? But so far, scaling it with data has proven to be pretty successful recipe for what we have achieved today. Now, the question is, what about what we want to achieve tomorrow, right? And there we might, we certainly will have some advances. Yes, please.
Why do you think transformers took so long to be discovered, for instance? I think there are specific barriers. The book has a few comments at the end. Do you have any comments on that? Why?
Yeah. Yeah, so first of all, I think that when you look into bits and pieces of transformer, it's something that has actually been around, like, right, feed-forward neural network has been around for decades. And then I have talked about attention, the way we have introduced it in recurrent neural networks. And self-attention is basically an extension of that idea. So I would say that lots of bits and pieces of transformers were already around, and it took putting them all together to, achieve the transformer in 2017. Now, I think there was one key advantage in 2017 that I can't tell you whether this is true, truly was motivation. But what is important about transformers is that unlike RNNs that need to produce everything sequentially, token by token, you can produce every token's representation in pair, right? And that gives you huge training efficiency. When you have better training efficiency, that means that you can use much more data, because then you can scale in a reasonable amount of time. So I think also advances in hardware was what motivated transformers, because potentially at that point, researchers were like, okay, we have this compute, now we are good with GPUs. How do we maximize the budget, the computational budget? And this idea that you can create representations of every token in parallel maximizes the budget, right? So this part hasn't been changed yet. And I think it's as long as you have transformers working at the scale, if you want to replace it, you need to find something else that works at scale.
Some people have said that we will never go back to using straight symbolic logic because big data will always be more accurate and get better results. Do you think that's true, or how would you respond to that? And then similarly, how would you respond to people who are currently proposing and pushing forward symbolic methods?
Yeah, so I think purely symbolic, no sense of these representations. I don't think that has any place whatsoever in the modern application areas. You need this notion that there is that the word that you can represent it with a vector, with a distribution, and that's always going to be better than representing words just by its pure, like surface form, it's simple. Now, combination of symbolic approaches with these more distribution approaches, that's an active area of research. I don't think there is a clear answer to that question yet. But there is no reason to completely say, okay, we should completely let that go either. If you ask Professor Srikumar, he will certainly have more to say about the combination of symbolic and neural approaches. But I don't have super strong thoughts about that. I think it's a very nice, compelling idea, and it would be amazing if it works. So far, introducing logic and rules maybe can work for problems where you don't have abundance of data. But if you are in cases where you have abundance of data, models so far have been quite capable of learning rules implicitly through the data. So, yeah, that's as much as I say.
Then one last question, will we cover any multimodal approaches as files? Or
yeah, so I'm not sure. Basically, we are so out of time that I can't confirm whether we will. Last year, I did talk about how do we produce vision and language models, or audio and language models, how people go about creating those, which is basically, today we are going to learn about pre-training and how do you again take transformer and mix it with the right pre-training data. How do you do tokenization? Now we, dissect images in a sequence of patches and all sorts of weird things. But really depends on the time. That's not the most important topic for us here. However, Professor Kenneth Marino will have a course on vision and language agents next semester. So that's going to build quite heavily on vision and language foundation models. So I highly recommend enrolling in that course if you're interested in more multimodal approaches. Yeah. Okay, let's get going because we have lots to cover today. So one thing that might have been unclear and or kind of lost is like, why have we talked about transformer for such a long time? And the reason why we talked about transformer in such a long, for such a long time is because it's going to be our basically standard approach for many, many applications in NLP and beyond. So you will have your transformer architecture, that's your neural architecture, and you will have some data, and you are going to combine this data with your transformer architecture. Right now, still focus on training with gradient descent. Later, we are going to start about prompting, getting outputs without actually changing the model weights. For now, I know you all know what prompting is because you use ChatGPT. Just let that go for a second. We will come to large language models. Right now, just focus on, we have a neural architecture and we have some label data. By training this architecture on this data, we can solve many problems. One thing that's going to become a super important ingredient is that we are not going to start training our transformer architecture by using some random weights that we have initialized using Xavier initialization anymore. Rather, we are going to start from a transformer version whose weight parameters have already been changed to some value during a stage we call pretraining. And this is going to be, or has been shown to be immensely important because basically what happens during pretraining, we learn a bunch of useful features that are transferable to many other tasks. This is called transfer learning. And if you want to think about this more in an optimization space, then you can imagine you have your loss landscape. And with pre-training, you have ended up in a better part of that loss landscape where you are less likely to go into local minimum saddle points. Either way, it's hugely important. So for us in this course, taking a pre-training model and then continue training it with labeled data is almost going to be like a Swiss Army knife for everything we want to do. So it's one approach, but we are going to talk about how we can use it for question answering. How can we use it for retrieval? How can we use it for summarization, translation, and so on? That's why we had this massive buildup to this place in the course where we are today, because this is basically our solution for many applications, okay? So first, as an overview, in a pre-training stage, you are going to have a huge collection of unlabeled text. So, for example, you develop a web crawler and you are going to crawl the entirety of the web, and that's going to produce a collection of written data. Okay? And then you need to think, okay, I don't want to label this data. I don't want to hire a bunch of annotators that look through this data because I have hundreds of gigabytes of this data, right? So you want to use objectives, training objectives that enable you to learn useful features of language without labeling any of the data. Knowing what you know from this course, what is one example of a task of that kind, where you can use unlabeled data and do some training for that specific task? Yeah, please.
Classification.
Classification. Why do you think classification? Well, wouldn't that require labeling data?
It could, but if you're using similarity, like,
That's my thought process was, if you did like guided training, then you would idea of similarity, like similar words are like similar areas that would learn that, like, oh, if you keep these as good in this section, and learn words in that section also are similar to this, right? But I guess with guided training, with 8 labels, even if you are like manually.
Yeah. Anything else? Yeah.
and hiding and predicting next words.
Hiding and predicting. Okay, that seems like you have known something from before I have said it. That's one option. Another option that we have actually learned in this course. Yes, please. Tokenization serves for tokens in text. I'm asking what kind of training objectives we can use to change the weight of the transformer, such that we use the unlabeled data, and we don't label it, we don't hire any people, but we can still use this unlabeled data and do a particular task.
Mask language modeling.
Mask language modeling is as well, hidden language modeling, something I haven't talked about, of course, yet. Just like regular language modeling, it's right there in our large language models, right? So we have learned language modeling, which I will repeat, because it seems like we need some reminder. Is the task of predicting the next token given a token so far, right? And we have introduced it previously for both analog language models and neural language models. From there, we extended it into conditional language modeling, and so now yada yada, right? So it's a great task here as well, right? We have some huge collection of text. I can take that collection of text, take one document, and I can then train my model to produce a next token given what we have seen so far. So I can just slide some, extend my context and be predicting next token, right? It's hugely important for me that you understand that this doesn't require any visualizing data. Okay, so just try to visualize this process. You are a developer who is training a language model by using a transformer, right? You don't need to hire anyone to do anything with that crawl of the data, right? It's already there. You're still approaching this as a supervised deep learning because you're predicting what the next token is, and you're using the actual token that had appeared in the data as your supervision, right? But it's not supervised in a sense that you needed to label any data. So this is sometimes called self-supervised learning as well. Okay, are there any doubts about this? This is a crucial bit that we simply can't go further in the course without you understanding this part. Yes,
And what does the term mask language modeling refer to?
I'm gonna come to that. So hold on to that for a second. Yeah.
And will we also cover, will we cover more methods of natural language processing, including unsupervised methods?
Maybe, I don't know, depends what exactly you have in mind. Let's keep off that question for later. Okay. So we do that. Again, this is just an overview. We are going to go into details. Once you're done with that, you have a transformer, you have its weights. They're not random weights anymore. They're weights that are good for the task of language modeling, right? And to do a task of language modeling, turns out you need to use many useful features of language, right? And now we can take that transformer model and we can continue training it for the task we actually want to solve. So for example, let's say we are looking into the task we have started this course with, sentiment classification. Again, in your homeworks, you had SST data with movie reviews which had a positive or negative label. Imagine I give you again that data. What you would do here is then take this pre-trained transformer model and continue training it using your standard negative log likelihood training and that data, right? So you just want to choose change random weights. You will change those weights that have been found during pre-training. So this second stage, although now we call it fine-tuning because you're fine-tuning the pre-trained model, is basically our standard supervised deep learning. There is nothing new or special or unknown for you there. You still use negative log likelihood training. You still change your weights with your some version of gradient descent algorithm and so on. Okay? Yeah.
So this pre-training phase, we want to stick to a task that doesn't require labeling. But then once we've done that pre-training, we can do whatever task we want. That can include tasks that require labeled data classification.
Yeah.
Okay.
Yeah, exactly. Okay. So this is a general overview. Now we are going to go into different ways ways we can do this, and some students have already hinted there's something like mask language modeling, which we actually didn't talk about yet. So we are going to see how to use that pre-training objective. We are going to see how to use our standard language one. Here, I planned that you already know a lot, and I didn't prepare that we walk through every single detail. I now think you know what language modeling is. That might have been a mistake. So we won't go into every single detail. That wasn't my plan. But if you feel like you would benefit for a little bit more detail, please stop me and we can go over it in more depth. Okay, so just to repeat what pre-training is. Pre-training is the process of teaching some model. For us, from now to the end of this course, that's going to be a transformer-based model. We want to teach it some general language patterns from large unlabeled data. Okay, so for us, because this is NLP, we are talking about a large corpus, a large collection of written text. Pretraining is a form of transfer learning. We are reusing knowledge learned from one task, namely language modeling, or soon to learn mask language modeling, to improve performance on some other task. For example, sentiment classification, right? We could have always, stick with the randomly initialized transformer. But if we do this form of transfer learning, we are going to improve performance on all these downstream tasks. Pre-training is something that most of us will never do. Okay, you'll do it only if you're hired in a big lab and you end up in a pre-training team. Likelihoods, I don't know. Whether you want to do this, also not sure whether you want to do this. So more or less, none of us will actually do pre-training in our lives. What we are going to do, we are going to use transformer models that have been pre-trained by someone else and were actually released publicly. Nowadays, there are many transformer-based foundation models that are not released. We say they are proprietary. So GPT-5, proprietary, Claude, proprietary, Gemini, proprietary, and so on. Those models we can use only through APIs. And typically we will not fine-tune them, we will prompt them, which is a topic for another day. Okay. But I have shown you Hugging Face's ecosystem. There you have millions of models. Those are open weight large language models. Open weight doesn't mean open. Open these days means that you release not only the weights of the model, but the data you use for pre-training, the code, and so on. And there is maybe a handful of organizations that have fully open LLMs. So for open-based LLMs, we are going to go to Hugging Face and use their code to load those weights and use their codes to continue training those models. And I will show a little bit of that today. Fine-tuning, on the other hand, is you can think about it as just supervised deep learning. I take my transformer and I train it with data. So really, it has a name, fine-tuning, but it's nothing special and nothing you don't know already, okay? So this is just a process of specializing our pre-trained model for a specific task using labeled data, okay? And when we say fine-tuning, because I will repeat that when I start talking about prompting, fine-tuning should always invoke in you that you do change the parameters or weights of the model, okay? So you need to have access to those. You can't fine-tune a model whose weights you don't have access to. Last time I also showed this tree of various language models, pre-trained language models, and I told you we have started with encoder-based transformers, and now these days we mostly have decoder-only transformers, and how we pre-trained encoder-only transformers is not how we are training decoder-only transformers. So I'm going to start not historically, where we started, encoder-only with mask language modeling. Rather, I'm going to start with decoder-only and language modeling, because you do know what language modeling is. And then we're going to see what did we do in about 2018, which are these BERT-based models. Okay, so there are three important things here. Transformer type, pre-training objective, and what's our so-called fine-tuning head. I will come to fine-tuning head in a second. I'm going to start with this configuration. I'm going to either take decoder only transformer. I could take encoder decoder. Not hugely important for us in this age 2025. Tomorrow might change. So I'm not going to talk a lot about encoder decoder transformers because we don't really use them today much. So I'm going to focus my explanation on decoder only transformers with language modeling pre-training objective. And then we are going to talk about LM or classification head. Okay, so first of all, remember that in 2017, the transformer was released and it was released like encoder decoder transformer. And then people realized, well, we don't really need to stick with this version of transformer. I can produce decoder only transformer where I basically strip the encoder part and I don't have cross attention anymore because I don't have anything to cross to, right? So this is decoder only GPT. And even if you have a conditional text generation task, you can still use decoder only one. Remember that decoder part of transformer is a part that's responsible for generate, right? However, let's say I have few tokens of my source sequence. I want to translate it, for example. Nothing stops me, right, to passing it through the decoder part and just not generating anything, right? I just need its representations. And then I can go to the next token, use whatever is the second token in the source sequence, again, produce a stack of representations for the second token. I don't care what the model will generate there because I'm encoding the source sequence, okay? So nothing stops you from passing the source sequence to learn the representations of those tokens, and then starting to generate once you have been done with encoding the source sequence. Is this clear? I know it's maybe a little bit vague. I feel like this is much clearer when you implement things, so you can be like, I'm just gonna use the output of this block of code. Yeah.
So how is the input sequence being encoded? We don't have an encoder block in the decoder only model.
Okay, so I see it's not really something you can imagine that easily. So remember that our decoder, right? Decoder is a set of decoder blocks. After each decoder block, we are going to have representation of the sequence we have generated so far, right? That's how we kind of introduce decoder, right? However, I could place my source token here, right? And it's going to produce some representation for it. And then it should predict what the next token is, right? But I can ignore that, right? I can completely ignore what the model thinks next token is going to be, right? Similarly to teacher force, and I can move to the next sequence, to the next token in the source sequence, right? And I'm going to get some vector for it again. My output layer, I just ignore. I don't do anything with it, right? And so on. So at some point, I'm going to plug in all my source tokens, and I'm going to have representation for each one of them. And now it's time for me to start decoding, actually doing the next token prediction. Let's imagine we have special end of source token. This is indication to your decoder, okay, this is where generation is going to be truly like I need to produce new text. You again have some representation, and now you actually care about next token. Now you can place it here. If this is the token you have generated, you can place it in the queue, okay?
So that input, when we do this actual decoding phase,
Mm-hmm.
is that going to be the next token that was generated from that final sequence? Or are we taking those vector representations and having that as input for our generation step?
No, there is no reason to place them as an inputs here, right? So this is almost like simulating with your decoder as if it has created a source sequence and now it needs to generate the target sequence.
I guess I'm just a bit confused as to what is the inputs, because at least as far as I'm seeing it, we're essentially using the decoder like an encoder to get those vector representations of our source sequence. But then what do we do with those vector representations of the source sequence? Are they used as inputs or what do we use them for then? If
I
not
see what
inputs?
you mean. What does self-attention use? Or causal attention here? It's always going to use a representation of all other tokens here, right? So you need representations of the source tokens because when you come to your causal or mask attention at this new target token, it's going to have ability to at every block to look at the corresponding representations of these other previous tokens, right? We are going to encode these as query keys and values, right? So we are going to change the representation of this one based on the attention weights we get from the causal attention, and then we are going to integrate parts of representation of these ones in the representation of this one through the standard query key transpose times value matrix.
So what is the input T1 there? What would that be in the example of, some sort of prompt that's given? We have our source sequence that ends at EOS. What's then the next input to the decoder?
So instead of answering your question, I will ask you, what do we do with language modeling?
We predict the next token.
Right, so here we predicted some token. And then remember, if we are training the model, we always have those two options between teacher forcing or using the actually generated token. At the inference time, we always must use the generated token, right?
Okay.
So if you are at the inference time, then here you would use the token you have actually predicted or sampled as to be the next one, okay?
Okay.
This is a standard language model, so
Okay.
there is nothing new there.
When we're putting our source tokens through the decoder, will they go through the mask multi-head attention, which means that one source token could look at token
Previous. Oh, you mean for these ones, do we allow the not causal, but rather bidirectional, where they can look both in the previous and the future source tokens?
Yeah, because when we're putting the self-attention and the token in the source sequence,
Yeah.
whereas if it seems like if you do this way, some token can be running in what other tokens can look at.
Yeah, I think you could do that, and that's probably maybe even a good idea. As far as I know, we don't do that, although I'm not 100% sure. I think we just use decoder as is, right, for encoding the source sequence. But yes, in theory, you could do that and then switch to the causal attention once you start decoding within the decoder. But I think it's going to always be, for the simplicity of coding everything, just the mask attention. Yeah, but I'll double check that. Yeah. That's a good question. Okay, so decoder, although there is no encoder, it can still produce representations of every token that's given in the input. That can be source sequence token that we are, kind of constraining the generation on, or it can be the actual token we have generated, or if we are doing teacher forcing, it can be the tokens, target tokens we have observed. So plenty of options. Okay, so we are going to start with to pre-train a decoder-only transformer. We are going to start with a very large corpus that's going to be deduplicated and filtered for quality. We are going to hopefully talk about pre-training data more today later. And initially, our transformers will be randomly initialized. So remember, we have a bunch of weight matrices in transformers. We have many weight matrices for query keys, values, as many as there are attention heads in each block, and then as many as there are blocks in the transformer. And then we have output like feed-forward layers. They have their own weight matrices. Initially, they are all going to be randomly initialized. And then we are going to use that data to predict the next token. So I have my written text, and I can start from BOS tokens, beginning of sequence, and I can train it to predict the next token and pretend that whatever was the next token I'm going to pretend that's what the model should have used, although it's a weird concept because we are starting to generate out of nothing. So again, you have your negative log likelihood training, which means that we are having a negative log of probability of true token, meaning the one that had been observed as the next token in the data, given whatever is in the input. Again, in the input can be true tokens if we are doing the feature forcing, or they can be generated tokens if we are not doing feature forcing. And there is going to be so much data in English that we are actually never going to see a same sequence twice. That's the goal, actually, because it has been shown that models, if you give it same sequence multiple times, there is higher likelihood if they are going to memorize it verbatim. And this has, first of all, you are killing the generalization power of your transformer model. But another problem is the copyright issues that you might have heard of, and we are going to also talk, hopefully, a little bit today. Okay, now we have fine-tuned, we have pre-trained the transformer-based decoder-only model with, imagine we have with language modeling objective. And now we download the weights from Hugging Face. What do we do? So we are going to have some input, as always. This input is going to be tokenized with some tokenized subword tokenizer. Each token is going to get its token embedding, and then we are not using positional embeddings. We are going to put them somewhere in a row. Everything goes through the decoder, right? And we get the representation of every token that is in the input as a kind of semi-final area. And now we have our output layer, which has been also pre-trained, right? It is that linear projection to the vector of the size of the vocabulary. And with decoder, very often we are going to frame any task as a sequence-to-sequence task and reuse that output layer, right? I mean, we can continue training it, but it's also going to be not replaced by something completely new, which is another option I'm going to talk about. So you take the entirety of your decoder-based transformer, and you change all of its weights, including the output layer. Now, the question is, how can we approach, let's say, text classification, which is not in itself sequence-to-sequence task, as a sequence-to-sequence task? Well, we can, instead of replacing our labels with 0 and 1, we can choose words in a vocabulary that should be generated to say this is positive or negative class. Logical choices are positive and negative, right? Like if we are doing sentiment classification. So I can fine-tune, meaning train my model to given whatever input I have given it here, I can train it to generate word positive if this was positive movie review, right? So it should use its output layer, which is this vocab size times D, to give me very high value for word positive. And then it generates word positive, right? Which is quite different from how we approach classification before, which is to use, instead of vocabulary size vectors, we had number of classes vectors to make these decisions. However, there is also an option that you say, well, thanks to the developers for giving me this output layer, but I'm going to train my own. I'm gonna reuse everything they have created up to the output layer. But then before output layer, I'm going to actually create new output layer. I'm going to randomly initialize it, and I'm going to train it from scratch. This is called introducing a new classification head. And this terminology head has then been also kind of emerging with this paradigm. So today, if I tell you, oh, I'm using classification head, this means that you are changing that output layer that was created to generate tokens with a new layer for specializing for whatever task you have in mind. And we're going to have other slides that visualize this a little bit better because that's going to be the only approach we have for encoder-based models. If I say, oh, I'm using LM head, language modeling head, that means that I'm sticking around with this pre-trained output layer, which gives me the distribution over the board. Okay. So there is not much technically here in terms of architecture. What is new for you is that you can now frame classification and other tasks that are not inherent in sequence-to-sequence tasks as sequence-to-sequence tasks and generate labels rather than predicting them. Okay, so this is just a visualization of our language modeling head. With language modeling head, we are going to have here, you see how I colored the last token in the input blue? This is because that representation of the last token in the input is special. We are going to take that representation and multiply that one with our matrix that's going to produce the logits, right? Which is, of course, matrix of the size of the vocab times the dimensionality of our representations. And we are going to get our logits vector, apply softmax to get distribution. And then we know we have options for sampling. If we are dealing with tasks like classification, frame, and sequence to sequence, we are typically going to use something that's more like greedy decoding or beam search rather than nucleus sampling, where we embrace the diversity. Here we want to more like, I just want the same thing all the time, whatever the model is the most sure about. I have also emphasized here something called auto model for causal LM. This is important for Hugging Face's ecosystem. So in Hugging Face, I will go over that a little bit. We are going to use these auto classes. And what those auto classes will do for us is that we don't need to think about, I'm using a specific decoder only transformer, and I want to use the LM head. Rather, we just need to know, I should use auto model for causal LM. I should give a name of my model, and then somewhere in the backend, Hugging Face's library is going to figure out which specific code should use. It's going to find, let's say if I'm using GPT-2 as my model, it's going to find out where its GPT-2 class is written and then use that code. So you don't need to think about all of those things, but you do need to remember, all right, if I'm gonna fine tune the pre-trained LM head, I need to use auto model for causal LM. That's something you do need to remember. Okay, and then a bunch of models you all know about or care to know about are the decoder-only transformers. So starting from GPT-3 in 2020, all the way to ChatGPT, which is powered by GPT-4, GPT-5, Claude, and so on. So all the big proprietary models you know are decoder-only transformers. Okay, now I want to move on to these other kinds of transformer models and pre-training that should be less familiar to you. But let's go just back to this slide and see whether this is clear. Yeah.
Why would someone want to use a new classification head, not using the output weight matrix that we generated?
Yeah, there are two reasons. First of all, if you are doing fine tuning, output LM head makes a huge chunk of parameters because the vocab size is usually 30 K or more, your bunch of parameters are gonna be in that matrix, right? So that's a lot of parameters to change if you're doing fine tuning. And maybe you have enough data, maybe you have thousands of data points, and you have maybe only 3 classes, right? That would mean that with new head, you need to randomly initialize a matrix of the size 3 classes times your dimensionality. So let's say 3,000 parameters instead of 10,000 times less than with the full LM head. And maybe you then realize, all right, so that's less parameters to train, and I have enough data to train it. And you also have a little bit more control later on, namely, with sequence to sequence, training everything to sequence, although you are training the model to produce, I don't know, positive token, positive, like word positive, to say this is a positive class, it still has option to generate some other word that you haven't reserved for these classes. So what sometimes people also do is instead of, imagine this is my vocabulary size times D. This is the output layer with the head. I get the vector of the size of the vocab. You could look at what is the highest value in this vector, but sometimes people say, well, I have reserved 2 tokens to represent my classes. Let's say 0 here, let's say that is here the first dimension corresponds to positive class, and I don't know, dimension 98 is negative. Instead of looking at any other probabilities, you just compare these two and you pick as the prediction, the one which is higher. And this is, people do this, sorry, I'm kind of now answering another question to answer your question, but people have started to do this because they have noticed that although they are training the model to generate either positive or negative, the model might still generate, I don't know, something else, some other token. And then you don't have a class for that, and that causes you issues. You don't know how to classify that input anymore. So instead, you can just look at those dimensions corresponding to tokens for which you assigned classes.
And that would be why you'd want to do that as opposed to doing a sequence to sequence task?
Yeah, basically with having dedicated, matrix output layer just for your classes, you don't have any of these issues, right? You are, it's going to always predict one of the classes that you have set to choose. Yeah.
Okay.
Yeah, but I would say the number of parameters is a bigger one.
Got it.
Yeah. Yeah.
I think it's kind of implied, but I just want to be sure, the dimensionality of your classification is number of classes, right?
Number of classes by the dimensionality of the vector. That's what's going to be, yes, in this here. Yeah. So with the 30,000 vocab of 30K is at minimum what we use today, and 4,000 is one among smaller dimensionality sizes. That's a lot of parameters, right? And seeing 100K for vocab size isn't crazy, right? So you can easily have with the smaller open weight models like 400,000 parameters just in that layer. Whereas if I have used new classification head, then if I have 2 classes with this size of hidden dimension 4K, I would have only 8,000 parameters to train versus again 400,000, which is much, much more. That's kind of what I'm trying to emphasize. Okay, now, before we have been using language modeling and as a pre-training objective with decoder-only models, we have been using something slightly different. We have been using encoder-only transformers and mask language model. And here, you might immediately ask me, well, how can we generate anything with encoder-only transformer? And we can't. Basically, at that point of time, we didn't care as much about text generation, which I know it's crazy now that we have ChatGPT. At that point, people were doing mostly classification-based tasks, and it's not like they didn't care, but it wasn't the main focus to do text generation. Like the idea of chatbots wasn't so obvious at the time. So here, we are going to take our encoder part of our transformers, meaning that our attention will be bidirectional. We can look into before the token and after the token, right? We don't have cross attention because we never had it in the encoder, and we are not predicting the next token. However, how these encoder-only transformers were trained was with mask language modeling object, which works by randomly sampling about 15% of input tokens and replacing them by a special mask token. Then you pass this kind of corrupted input through this encoder-based transformer. And as always, we are going to get the token representation of each one of these tokens in the input, including the mask token. So what you can do is that take the final representation of your mask token, one of them, I mean each one of them, but for now single out one of them, and try to predict which token was in its place. This is trying to kind of simulate that your representation of the input, that token, where you had mask information, should kind of have information about what's around it, which is a useful feature, and then by that to predict what the mask token was. So you can get the losses at each one of these mask tokens representation, and then you can average them and backprop, right? And this is how the mask language modeling is going to work. Instead of trying to predict what's the next token to come, you're trying to predict what was the token originally in place of the mask token. When you fine-tune a mask MLM pre-trained model, you're going to use these special tokens called CLS and separator tokens. CLS token is going to be placed at the beginning of your sequence, and separator token has been used to separate different parts of the inputs. So sometimes, for example, if you want to measure similarity between two sentences or two paragraphs, you would put separator token in between whatever are two distinct parts of that text. And you will always finish with the separator token too. So see here at the end, we have a separator token as well. Okay, so you place these special tokens. They have their vocabulary, they have their input token embeddings, they have everything other tokens have. You're going to then just fine-tune your model, meaning change the pre-trained weights using negative log likelihood training loss and the gradient descent algorithm. And that's basically it, nothing special. However, at the classification time, so when you do your classification, you are going to introduce that new classification head. So this is just a visualization. You have your input with CLS and separator token. You pass it through BERT, and then the final representation of the CLS token is highlighted, which might not be super well visible here, but that's the one that we are using as the representation of the entire sequence. A little question for you. Why is it okay to use representation of the CLS token in place of the entire input? What enables that in the transformer architecture? Yeah. Self-attention, right? With self-attention, one token gets information about all the other tokens. And we are going to train our pre-trained model with a special CLS token and then use that CLS token to do something. eventually the model will pick up that this is also some kind of important token, and self-attention has power to add in that token as much as it wants, right? So one token can always serve as a representation of the entire sequence because self-attention allows us to put whatever we want into single tokens representation. Yeah.
Correct me if I'm wrong though, but when we did the self-attention, we were processing each token sequentially. So as far as I understood, the last token in the sequence is something that would be sort of getting information from everything that came before. So why wouldn't we use the SEP tokens representation as our first, as our inputs?
So what you said is true for decoder only transformer. So only in decoder transformer model, last token in the input sees everything before it. But in encoder-based transformers, every token sees every token because the attention is bidirectional, self-attention. It's not causal or mass attention.
Oh, right.
Now, I think that's something a detail you forgot, but you are not wrong that we could have used this last one, right? It just happens that people who created this, they have decided that the first one is going to be special. But I think you could have easily put CLS at the end and it would work. I don't think it's super important.
Okay.
Yeah. Okay, so we take the representation of the CLS token and we are going to introduce our new classification head. So in this visualization, they are almost talking about two separate models. Don't think about them as a fully separate models because that's all part of the same model that you're going to train. It's connected, so back propagation grows smoothly across the entire stack to the bottom. But what I wanted to emphasize is that once you have your representation of your CLS token, more or less what you do is logistic regression, nothing special, right? So you have your transformation to the vector of number of classes plus softmax, and then you do something. So this is an important part. With encoder-only transformers trained with mask language modeling, we never use the pre-trained output layer. It's useful only for generating a mask token. And although you can design weird prompts where you say, I don't know, movie review, then you say, this movie review is mask, you can kind of try to predict what's in the mask. And this is how we did early prompting. Turns out that next token prediction is way easier way to do this. So you would today never actually use the pre-trained output layer specialized for mask language model. It basically has no major purpose unless you want to do weird prompting. So with encoder-only transformer pre-trained with mask language modeling, almost always you use new classification head, which now I repeat, means that you ditch your output layer that you have and you replace it with a new output layer. That new output layer, as always in this course, is going to involve a linear transformation to a vector of the size of the number of classes. So we take some vector representing the input. Here, that's going to be the last representation of the CLS token. And we multiply it with the weight matrix of the size number of classes times dimensionality, or here transposed, right? And then you get your vector of the size of number of classes, apply softmax. And because this is not generation and we don't care about diversity and surrounding cumuli, here you are always going to use the highest probability label as you want to predict. Important to embrace here is that these values are initially random when we start fine-tuning. These are new parameters, right? So we need to train this from scratch, unlike the rest of the transformer. So you do need data for this approach. And I'm emphasizing this because once we start about prompting and not using fine-tuning, this is important to know that you can't use this because there are new parameters here that you need to learn, okay? Okay, so I'm going to repeat. New classification head can be used both with decoder-only transformers and with encoder-only transformer. In encoder-only transformer, pre-trained with mask language modeling, we are going to take the final token representation of the CLS token as the representation of the entire input. With decoder-only transformers, we are going to take the final token in the input, its final representation. So slightly different. Whatever is that choice of the vector, new classification head always involves new weight matrix of the shape number of classes times d, or other way around if you transpose it, and so on. Everything else is super familiar for you. You have implemented it in the second and first cycle. Now here, notice that I have auto model for sequence classification. And this is what I meant previously when I said you need to pay a little bit of attention of which auto class you are going to use. So for example, I'm going to try to show you that in the hand-face demo. But if I use the same model, let's say GPT-2, I can use it, I can load it by using from pre-train. And then I can decide to do classification, and I can do classification with the same pre-trained transformer by using auto model for sequence classification, which would then create this new classification head for me. It would initialize this weight matrix and so on. And I can use it. I don't need to write that bit for myself. With causal LM auto class, we are basically going to reuse the old LM head, and we are going to work with that one. Okay, this is just yet another visualization of what we're talking about. Here we are pre-training by masking some input token and trying to reconstruct it. At the fine-tuning stage, we take everything except the last layer of our pre-trained transformer, which we replace with new head, and then we change the weights of everything using negative log likelihood for auto classification. Yeah.
How big of an issue is gradient explosion? Are you typically like raising certain layers when you're doing the fine tuning, or?
Gradients become less of an issue with any kinds of weird stuff with gradients, right? There aren't really an issue with transformer. However, I have a funky story to share. At some point, some of my colleagues and some other people have written these papers on stability of one of these models called BERT. This was the first model that has been pre-trained with mask language modeling, and by fine-tuning it, there were such tremendous improvements over the baseline. So it was a very important model. To this date, it's a very important model. And what these researchers have found that if you are doing classification for some specific task with BERT, and do multiple runs, meaning you just change the random seed, and that's all you change, you get widely different results. And that was the problem of stability. Everyone was talking about how this is hugely unstable. And then people have done a little bit more of exploration, and then a really cool paper has been released that have attributed everything back to Adam. And they had said, well, for some reason, developers in Google who created BERT have turned off one of the Adam's parameters. Remember, I mentioned there are two basically that indicates the second momentum. And they have turned it off, and now gradients in the beginning of training have become huge, and everything was unstable. And for me, I was like, why would I ever turn off the component of most used algorithm there is in machine learning? So it sounds like Twitter action. I don't know how I managed to come to people who actually were on the team, and they told me that they couldn't distribute the model without turning off that specific parameter of the Adam. So basically, they couldn't parallelize things. They're like, screw it, turn off the Adam, train everything. I mean, it was hugely successful in many other ways, but it did result with the huge stability issues. So although you will see some papers around that time, 2019, 2020, that do talk about stability issues, I think those have been largely fixed, I would say, for these kinds of models, yeah. Yeah,
On the same thing, I feel like one issue, if you look at it, is training time, like if you freeze the whole transformer and only update the MLT.
yeah, okay, that's for me, it's not an issue, right? I mean, it is an issue that it's slow, training time is slow, and can you do different, more smarter, more efficient training? So we are going to talk about parameter efficient fine tuning. We're going to talk a little bit about LoRa and QLoRa. So of course, yeah, training time, especially the larger these models become, is a huge issue, and not just training time, but the memory you need to save these models. I won't test you on this because I decided to drop the last homework, but for example, last time I was teaching this course and I can share this exercise with you. I had students try how much, there was a family of twin models of different sizes, so 1 billion, 2 billion, 3 billion, and I just asked them, given the memory you have on a column, when do you hit CUDA out of memory? You hit it real soon, right? But then they needed to kind of think about how much memory they have and how much parameters they can fit. And this is a nice exercise to think about how larger these models become, more memory you need, and your memory doesn't increase on CHPC magically, so you are bounded with what you can fit. But then when you're smart about how you quantize the model and you use lower precision and all of these tricks and bits, you can fit a way larger model than a full precision model and without full training of the model on the CHPC. And do actually fine tuning of pretty large models as well. Yeah, but that's another topic. I wouldn't think about it as like a buggy issue. You know what I mean? Okay, so there are different. Okay, as I mentioned, maybe now in this huge digression that was amongst first. I mean, the first model that had used mask language modeling, they introduced mask language modeling. And then since birth, there have been Roberta and Liberta. Basically, these are versions of this bird model that people have kind of created by stripping away unnecessary parts of bird. So I think it's mostly better to use Liberta rather than bird if you need a model for classification, let's say. But also, very recently, people have looked back and said, okay, we have now all used decoder-only models, and that's great, but like bird-based models still have a place in our application area. I will come to that in a second. So knowing all the tricks we have used, new tricks for decoder-only models and for pre-training with language modeling, they said, well, let's try to create a modern version of BERT. And they have done that. So if you ever need something like BERT, I think it's best to use this modern BERT version, which is should be much higher quality. Your question can be, why would I care to use a 2019 model today, right? Completely reasonable question. The reason why you still might want BERT-like models, like modern BERT, is if you have a classification problem. So you don't have text generation, you don't really need decoder-only model or encoder-decoder, right? For you, for your application, having capacity to generate, simply not important, right? So that's your application. And it turns out you have a lot of data for it. So you need to learn new classification path, not a huge issue. You have data to learn, right? Another reason why you will use for sure BERT in your lifetime, if you end up using, sticking with this space, is if you need a representation, a vector representation of piece of text, for whatever reason you want to do. So for example, we are very soon going to talk about retrieval. And to do retrieval, meaning given some queries, finding from a huge collection of other texts, which one is most relevant. for example, for the sake of searching. You will want to have a vector representation of each piece of text in your collection, and then you're going to use cosine similarity as a way to retrieve. And very often today, people are going to use some kind of BERT model in CLS representation at the final layer as a representation of input text. So whenever you feel like, oh, I just need to represent this text to do something with it, you'll probably want to go to some BERT-like version, and tools such as SBERT, which produce, or SentenceBERT, that produce these representations. So just because this has been created in 2019, 2018, just because it doesn't have a role for text generation anymore, just because this is not a large language model, doesn't mean it's not useful. If anything, a lot of applications, most applications will need this technology, okay? All right, let me use the last 2 minutes we have just to show you why this was a pivotal moment in recent history. So when BERT has been released in 2018, they have introduced mask language modeling, pre-training with mask language modeling and fine-tuning. And they have shown such dramatic increases in performance. One benchmark at the time was called GLUE. If you know what MMLU is today, that was GLUE of 2018. So basically just a collection of bunch of tasks. People were thinking, okay, this is a hard task at that point of time. So these were including something called NLI, where given some premise and hypothesis, you need to say whether hypothesis is contradicted by premise or it's entailed. So something like logical entailment. Here you have whether two questions are paraphrases of each other. Your SST, which are familiar now, sentiment classification. MRPC is another paraphrase detection kind of task. So a bunch of like various tasks, right? And being good at all of them was really hard at the time. So here at the bottom, you see BERT results. Here you see state of the art before OpenAI's GPT-1. That was a thing. It didn't even have one in front because they didn't probably know they'll have 2, 3, 4, 5. And then LSTM, which is an improved version of recurrent neural networks, together with attention and all of those bits and pieces that were successful at the time. Now, I won't go over each column for you to kind of see the differences. Maybe just look at the average. You can see that there has been substantial increase in accuracy with this approach. And this held for many of the tasks that people have found dear at the time. And this was a huge moment where we had this big improvement. So as a last thing to mention here, this was a moment also where we started to shift from what we have called classical NLP, where you have this classical pipeline of tokenizing input, then saying which grammatical role this word has. Is it a noun? Is it a verb? Is it adjective? Okay, is it a named entity? If it's a named entity, does it refer to organization, a person, blah, blah, blah. And so many manual features stacked together to make a decision. Now we have turned it all into just transformer makes you some representation and you make a prediction. But what people have found out, researchers have found out that if you poke into the layers of BERT, what you will find out is sensitivity to this linguistic phenomena. Basically, it encodes the notion of so-called part of speech tag, which grammatical role a token has, or whether it's named entity, named entity or not. So these features have all been implicitly captured, and basically by rediscovering this useful feature and useful pipeline, these models can solve many of these tasks. Okay, I had other things I want to talk about, and I really need to revisit how we're going to talk about everything I want to say in this course. But yeah, next time we are just going to, for sure, look a little bit into Hugging Face. That part is important. Okay, see you on Wednesday. Sorry for taking extra 2 minutes.